So the first of our Extension 2 topics, complex numbers. And we start off with what is actually a lie, but I'll explain that in a second. All right, let's look at solving quadratics. Here's a quadratic equation we'd like to solve. X squared plus 1 is equal to 0. X squared equals negative 1, and of course up till today we'd say, oh, well, there's no solutions. What we really should have said is there's no real solutions, because there are solutions. Right. So to solve it, we define a new number. That new number actually turns out to be a letter, and that letter is I, and I represents the square root of negative 1, or more accurately, I squared is negative 1. Okay, so I is the number that when we square it, we get the answer negative 1, and we call I an imaginary number. It's an unfortunate word. I mean, we could have called it anything, but they decided to call them imaginary numbers, and because people call them imaginary numbers, people think, oh, they don't exist because they're imaginary. They exist, just like negative numbers exist, and they do exist. It's just the name that's given to these numbers, imaginary numbers. Okay, so now we can solve it, because if we've got x squared equals negative 1, we know x will be plus or minus the square root of negative 1, and we know it's I, that when we square it, we get negative 1, so we have plus or minus I. I said it was a little bit of a lie. That's not why imaginary numbers were created. They actually were created so we could solve the general cubic. Right? The quadratic didn't actually present much of an issue, because we have our formula, x equals negative b plus or minus square, nice and easy. But they wanted to come up with a formula to solve all cubics, and they couldn't do it, because some of the solutions to cubics are also imaginary, and in order to do that, they needed to define this imaginary number. So it's a little fallacy we use, but it's a convenient way to introduce the square root of negative 1. So I have some definitions. All complex numbers we can say is written in the form Z is most commonly the pronumeral used when we're talking about complex numbers, and we can break it up into x plus IY. So it has two parts to it. Now, it has a real part and an imaginary part. So every number that we know of has two parts to it, a real part and an imaginary part. Even the numbers you have been working with your whole life have two parts to it, a real part and an imaginary part. It's just that up until now, the imaginary part is equal to 0. Well, now we're saying, well, it can equal other things. So notation, RE for real. So the real part of Z would be whatever X is. The imaginary part of Z would be whatever Y is. Now notice if they ask you, what is the imaginary part? You don't say it's IY, it's Y. The I is the symbol we've got before it to tell us that this is the imaginary part. So 3 plus 5i, if I was to answer this one, I'd say the real part is 3. The imaginary part is just 5. It's not 5i. The imaginary part is 5. If the real part is equal to 0, then that's what we call a pure imaginary number. Well, there's some examples. Root 3i, minus 6i, anything that's just a multiple i. What we're used to dealing with is when the imaginary part is equal to 0, and that is what we call real numbers. 3/4, pi, e, negative 4. They're all real numbers. And every complex number has a conjugate, because if you think about it, we're dealing with a surd here, because we said I squared was equal to negative 1. So in other words, I we can think of as the square root of negative 1. So what we really have there is a surd, x plus some multiple of the square root of negative 1. And just like surds have conjugates, well, complex numbers do, because they are surds. So x plus iy has a complex conjugate, x minus iy. We just change the sign in front of the surd. So z is minus 2 minus root 7i. Z, and you'll notice the notation I'm using there for conjugate is a horizontal bar above the Z. So that's the notation for conjugate. And it would be minus 2 plus the square root of 7i. All right, so here's the real world. In fact, the imaginary world as well. All of our numbers are complex numbers. The term complex numbers gets thrown around very loosely. I mean, as I say, really, all the numbers we've been dealing with are complex numbers. It's just when the imaginary part is equal to 0. But often when they say give the complex solutions, they're talking about the imaginary solutions. So inside our complex numbers, up until now, we had this set of real numbers. So all the ones where y was equal to 0. And over the years, since you've been dealing with numbers, we've learnt that, they can be broken up into all sorts of things. Now, there's this other set of numbers called the imaginary numbers. And they're the ones where y doesn't equal 0. Now, over there in the real ones, as we progress along, we learn about rational numbers, all the numbers that can be written as fractions. And there were irrational numbers, the ones that can't be written as fractions. So there's no point of intersection there. And then inside the rational numbers, because as I say, all the numbers that can be written as fractions, there's the ones that we think of traditionally as fractions, where you actually see them, 3/4, things like that. But we also have the integers. We don't normally think of integers as fractions. I mean, they are fractions. I mean, you'd say 7 is 7 over 1, but we think of them as integers, as different to fractions. And of course, inside the integers, we have the natural numbers, which are 1, 2, 3, 4. Then, of course, we have 0 as well, that really weird number that sort of sits by itself. But is it an integer? Does it exist? Well, that's a whole nother discussion we can have. And sort of overriding all these, we could have negative numbers as well, because we could have negative fractions, we could have negative integers, we could have negative irrational numbers, and so on. So all our real numbers can be broken down into all sorts of different types of numbers. So now we've got this new type of number, the imaginary numbers. And inside there, we've got our pure imaginary numbers. That's pretty much it. Okay? Because we can't break them up into rational and irrational, because I suppose theoretically, they're all irrational, because they all contain the square root of -1. And so you'll notice it's only the rational numbers that were broken down into fractions and things like that. So not a lot as far as classification of the type of imaginary numbers. Pretty much they're pure imaginary numbers, or they're just imaginary numbers. But the interesting thing about imaginary numbers is you can't order them. Because in order to be able to order them, I need to be able to put them on the number line. And I can't place imaginary numbers on the number line. There's no spot for them there. So I can't say 2 is bigger than I, if you like. I mean, it doesn't make sense. All right, how do we deal with these things? Well, the good news is basic operations we already know. We already know under 2 different ways of thinking about it. We can think of them like surds, and we know how to do the operations with surds, and we can think of them as algebra as well, because you can think of I like a pronumeral. So if I want to add them, there's 2 complex numbers, 4 minus 3i plus minus 8 plus 2i. It really is just like a piece of algebra. So it's minus 4 minus I, because they don't mix. So I can only add the real with the real and the imaginary with the imaginary. I can't join the 2 together. Same with subtraction. If I was to subtract them, again, just like algebra, we get 12 minus 5i. Multiplication becomes interesting though. Comes like a binomial product. Okay? So when I expand it out, I get this 6i squared. Now, we could say, well, yeah, all right, the 8i and the 24i, they'll add together. But this 6i squared I can simplify, because I know what I squared is. I squared is -1. So in fact, that is a real number, 6i squared. So I'm really saying plus 6. And so it ends up being minus 26 plus 32i. Now, when I'm actually writing this, working out down, I probably don't write down the line minus 6i squared. I probably just go straight to plus 6. But you just got to be careful, because I squared being negative, and then negative times negative is a positive, and so on. Now, division is where we realise the denominator. See, in surds, we rationalise the denominator. Okay? So if I got 4 minus 3i, and I want to divide it by minus 8 plus 2i, the only way I can get an answer where I can separate this fraction into a real part and imaginary part is if I've got a single number on the bottom. Because when you have a fraction with a plus b on the bottom, you can't separate the fraction. The denominator would have to stay the same. So the first thing we need to do is to make the bottom of this fraction one number. It makes sense to make it a real number. And so we do it by realising the denominator, which, just like rationalising the denominator, means multiplying by its conjugate. Because when you multiply by its conjugate, you have the difference of 2 squares on the bottom. And once you're dealing with squares, it's no longer imaginary. because I squared is negative 1. So when I'm dealing with imaginary numbers, we've got the difference of two squares, but it's actually the sum of two squares, right? Because I'll get minus 2i squared, but I squared is negative 1, and so it becomes plus 2. So the difference of two squares becomes the sum of two squares, 64 plus 4. On the bottom, 64 plus 4, obviously we can do, it's 68, and now I can split them up into a real part and an imaginary part. So it's minus 19 on 34 plus 8 on 34i. Now, unlike when we're dealing with surds, when we were dealing with surds, it was okay to leave a surd in the bottom. If I said, what's the sign of 45? 1 on root 2, and we're happy to leave it like that. The only time we used to rationalise the denominator was if we needed to compare the size of fractions and things like that. So again, it was convenient to make the bottom of the fraction a whole number. When it comes to complex numbers, we always realise the denominator. We never leave the imaginary part in the bottom. So some basic ideas about conjugates, which can sometimes help us with problems. The actual order that you do things in doesn't matter. So if I want to find the conjugate of Z1 plus Z2, I could add the two together first and then find the conjugate of that. Or I could find the conjugate of each individual number and then add those together. So it doesn't matter when I take the conjugate. I could do the addition first, or I could find the conjugates first. Same with multiplication, same with division. So all the operations, it does not matter when we take the conjugate. Do the operation first or take the conjugate first. If I multiply a number by its conjugate, and that's what we just saw on the bottom of the fraction, we get the sum of two squares. Not just any two squares, it's the real part squared plus the imaginary part squared. And if you want to find the reciprocal of a complex number, then it always will turn out to be the conjugate on z conjugate. Because if you think about it, look, the z conjugates cancel. So the very quick way of doing it is to say, oh, well, if I want to find the reciprocal, conjugate will go on top, and then I just got sum of two squares on the bottom. There's my answer. So if I want to find the reciprocal of 1 on 4 minus 3i, I say, okay, well, the conjugate is 4 plus 3i. On the bottom, sum of two squares, so 16 plus 9 is 25. And there's my answer. I found the reciprocal of that complex number. Equations. Okay. Nothing changes. All the rules of mathematics stay the same. But it's the real part must equal the real part, and the imaginary part must equal the imaginary part. Yeah, we don't mix the two. So in other words, if we've got two complex numbers we're comparing, and A1 plus B1i is the same as A2 plus B2i, the only possibility is that A1 equals A2 and B1 equals B2. So we just look at them like two separate equations, if you like. So here's a very simple one, I suppose. I could do it a couple of ways. I could expand the left-hand side out, or I could divide by the 2 plus 3i. However, but I want to make the x plus iy by itself. I've expanded the left-hand side out, and so I end up with two simultaneous equations. 2x minus 3y ends up being 4, because the real part must equal the real part, and 3x minus 2y is minus 2. Imaginary part must equal the imaginary part. Solve my simultaneous equations, and I get a value for x, and subbing back in a value for y. Now, z plus 2iw is 4 plus 3i. 2z plus iw is 3 plus 4i. Just like any other simultaneous equation, if we want to eliminate, we need to make the coefficient the same. The fact that there's imaginary numbers there doesn't change the idea. So I could either make the coefficient of z on the top one to be 2, or I could make the coefficient of the bottom one for w to be 2i. Just need them to be the same. So which way around did I go? I made the coefficients of w the same. So the bottom one now becomes 4z plus 2iw is 6 plus 8i. So if I subtract, 3z will be 2 plus 5i. So z is 2/3 plus 5/3 i. Substitute back in, and I've substituted in the very first one, z plus 2iw. Move to the other side. I now know that 2iw is 10 thirds plus 4 thirds I. So divide by 2I, and we end up with 2 thirds minus 5 thirds I. So the ideas are the same. Now, the mathematics hasn't changed. We're just dealing with this new type of number. So to start off with, we'll have a go at these.